Welcome to this explainer. Okay, picture this. You've just navigated a massive, floating structure all the way across the ocean. Transit complete, coordinates are in sight, but honestly, getting there was actually the easy part. Now comes the incredibly high-stakes, precision work of parking it exactly on its target on the ocean floor. And the margin for error here is essentially zero.
Okay, let's dive right into this. How in the world do you precisely park thousands of tons of steel in the middle of a constantly moving ocean? I mean, think about the enormous physical challenge we're dealing with. You're trying to push a giant, flak hull against relentless wind and tidal streams, completely relying on tugboats to hold this colossal structure perfectly still over an invisible mark beneath the waves.
So, here is our mission briefing. We're going to cover 1. The approach, 2. The blueprint, 3. The hold, 4. The touchdown, and 5. The physics of failure.
Starting off with Phase 1, the approach, battling the elements.
You see, the hull of a jackup rig presents this massive, flat surface area to the ocean. Because of that, a tidal stream moving at just 0.5 knots, which is barely a crawl really, generates huge forces. It acts almost like a giant, invisible hand pushing against the rig, requiring some serious, dedicated tug power to counteract the wind and currents just to hold the hull steady.
Moving on to Phase 2, the blueprint, maneuvering diagrams.
Now, you absolutely do not just wing an operation like this. The positioning strategy is dictated by the maneuvering diagram. Think of it as the ultimate, location-specific battle plan. The towmaster has to evaluate the prevailing wind, tidal stream speed, and the required drilling heading. But here's the catch, and what's really interesting about this, they can't just rely on a forecast. If the actual tide flowing under the rig is different from the prediction, well, the planned tub configuration is going to be totally useless. The towmaster must confirm that these variables match the actual conditions out there on the water.
Which brings us to Phase 3, the hold, freezing in place.
So, the tugs have fought the elements, and the hull is hovering right over those exact target coordinates. Now comes this incredibly precarious transition phase. The tugs have to freeze the rig perfectly in place while the heavy legs lower down into the water. Maintaining this hold requires absolutely flawless execution from 3 parties: the towmaster, the tug captains, and the jacking crew. Why is this triad so critical? Because as those heavy legs descend, the hull's center of gravity drastically changes, making the whole thing a lot less stable. Any breakdown in communication here means the leg lands in the wrong spot.
All right, Phase 4, the touchdown, making contact. This right here is the most delicate, nerve-wracking moment of the entire operation. In the offshore industry, they call this tagging the seabed. Basically, it's the initial, highly controlled lowering of the spud can, the foot of the leg, until it just gently touches the ocean floor. It takes surgical precision to confirm the depth and position without transferring any significant weight onto the leg just yet.
To actually pull off this gentle contact, the leg is lowered gradually, very slowly. The crew is intensely watching the jacking machinery's load cell readings, and this brilliantly illustrates how they do it. They confirm touchdown when there's a slight, expected load increase. You don't just assume contact based on mathematical depth charts or GPS coordinates. No, it is physically confirmed by watching that mechanical load shift as the spud can actually meets the earth.
Finally, Phase 5, the physics of failure, vessel motion limits. During this touchdown phase, the rules governing vessel motion, specifically heave, that's vertical motion, pitch, front to back, and roll, side to side, are totally non-negotiable. Imagine the hull is heaving downwards with an ocean wave exactly when the leg tags the seabed. Now, if you're over soft clay, the soil absorbs that dynamic impact, but if you're over a hard seabed, like rock or gravel, the earth doesn't budge. The full, multiplied shock load of the entire rig's dynamic energy is transferred instantaneously, straight back up the steel leg.
And the results of hitting a hard seabed during excessive heave or roll, they are catastrophic. It creates an immediate shock load to the machinery. We're talking the fracturing of jacking pinion teeth, cracking of heavy rack welds, and literally buckling the steel plates. And honestly, the scariest part is that it can cause hidden structural failures that you can't even see from the surface, which could fail disastrously later on when the rig actually attempts to elevate.
So, these limits are absolute. Let the severity of that rule really sink in for a second. If sea conditions produce motion that exceeds those specific limits, leg lowering has to be completely suspended. The crew must wait for the weather to improve. There is no rushing it, because the physics of failure here, they are entirely unforgiving.
So, the big takeaway from this explainer is that in a moving ocean, precision and immense patience are absolutely everything. Which leaves us with a pretty fascinating question to ponder. If simply tagging the seabed, just making that gentle initial contact, requires this much flawless precision and delicate maneuvering, how on earth do you safely shift thousands of tons of rig weight onto those tiny contact points during the heavy lifting of the preloading phase? That is a massive engineering feat to explore next time. Thanks for joining me for this explainer, and keep learning.